Okay, welcome everyone. So in this video, we are going to wrap up our treatment for now of bases. And there's one last matrix subspace that we haven't looked at. So we've looked at how we can find bases for the null space of a matrix and the column space of a matrix. We haven't discussed the row space of a matrix. And so just recall that the row space of a matrix is the subspace that we get when we look at linear combinations of the row vectors of a matrix. And so one way to consider the row space of a matrix A would be to take a look at the column space of the transpose of matrix A. So one way to talk about row spaces is to just take the transpose of a matrix and not define anything new, just talk about what we already discussed about column spaces. But we can work directly with matrix A to identify the row space of matrix A. So we're going to make an observation here that says if two matrices A and B are row equivalent, meaning I can use elementary row operations to get from one matrix to the other, then their row spaces are identical. They are exactly the same. And the basis that we find for the row space of matrix A is going to be identical. We can use the same basis for the row space of matrix B. So for example, if we have A is just some arbitrary matrix in no special particular form, and we're able to do some row operations on it and write it in form B, which is we're going to assume is row echelon form. Okay, we don't even need it to be reduced row echelon form. Then we can pick off any of the non-zero rows of this row echelon form matrix B. That's going to be a basis for the row space of matrix B. And since matrix B and A have the same row spaces, that's also going to be a row space for matrix A. So I think the best way to illustrate this really nice result is to just take a look at this example that we've been working with, where we started with this 4x5 matrix A, which was not in reduced form. If we use Python or do some elementary row operations on matrix A, we can verify that it's, here we actually have it in its reduced row echelon form over here, but you wouldn't even have to go that far. You could stop once you get the matrix in once it's in row echelon form. It's not that important that the pivots are equal to 1 or that we eliminate entries above the pivots. But this is great. We have found that there is a row echelon form, in fact, reduced row echelon form of matrix A, which is given over here. So this means I'm just going to pull off any of the non-zero rows of matrix B. Here's a non-zero row, here's a non-zero row, and here's another non-zero row. We have 3 of them. And these 3 row vectors are going to form a basis for the row space of matrix B, and therefore they also form the basis for a row space of matrix A, since matrix A is row equivalent to this reduced row echelon form over here. So therefore, basis for the row space of matrix A would be 1, 4, 0, 2, 0, 0, 0, 1, minus 1, 0, and then lastly 0, 0, 0, 0, 1. So this is going to be a subspace of the domain, which is R5. And notice the difference between row spaces and column spaces is that I didn't need to pick off the rows in the original matrix A. I used the actual rows over here in the reduced row echelon form of this row equivalent matrix that we have over here. So let me kind of summarize this distinction between how we need to be careful about finding bases for the row spaces and the column spaces in one last summary slide for this section. Okay, so let's summarize what we've uncovered about column spaces, about finding bases for column spaces, null spaces, and row spaces for a given m by n matrix A. So for the null space, we just solve the equation, the homogeneous matrix equation, AX is equal to 0, and we describe the solution set of that equation, and that solution set is going to form a basis for the null space. So for example, if we had this matrix A that we started with, yes, we definitely would want to put it in its reduced row echelon form to understand the solution set of this. And then we were able to kind of generate the solution set and write the basis for the null space of matrix A. When it comes to looking at the row space and the column space, we need to be a little bit careful. So when we're looking at the row space of matrix A, we do want to take this matrix and write it in row echelon form. Okay, we don't have to go all the way to reduced row echelon form, but that would do as well. So over here, we took matrix A, did some row operations. It's in reduced row echelon form, and then we identify the non-zero rows of that matrix, and all three of these non-zero rows, they made up the basis for the row space of A. And we don't pick the original rows over here. We're able to just use the rows right in the reduced row echelon form. When we're thinking about the column basis for matrix A, we do need to be more careful. So we do want to write this matrix in reduced row echelon form, and then we can identify where the pivots are. So there's a pivot in column 1. Again, there was a pivot in column 3, and there was a pivot in column 5. So our basis for the column space is not going to be columns in the reduced row echelon form matrix, but rather we go back to the original matrix A and pick off column 1, column 3, and column 5. And so now these three columns that I highlighted in green, this gives us a basis for the column space of matrix A.